It's a pleasure to be here, and I'm amazed to see so many of you, so many familiar faces and so many new faces. It's such a strange feeling to feel so much at home and at the same time so much having a new feeling. It's the first time I'm giving a public talk here, but I've been here for almost 18 years. Can you imagine? In fact, probably as much of a home as anywhere else I've been in my life. But here we are. We're going to talk about something else, not about me, a little bit about me, but more about the Big Bang. But I'm going to start with a question. And I want you to ponder on this question for a bit. So what is the oldest thing you can remember? And we're going to come back to this question, and we're going to try to explore this question and dig deeper and deeper in as many ways as we can. And I'm going to leave it as a homework for you to keep doing that going forward. There will be an exam next week, so just studying. And we're going to go up. Right, so what is the oldest thing you can remember? I'm going to start with the battles, and the first one is Battle of the Book. So, I got in 2018, so almost 6 years ago, this email from someone I never knew about, this very weird email, skydansfield@hotmail.co.uk. It misspelled my name. It said, I'm a producer of a series of educational not-for-profit films made for YouTube exploring competing models of the early universe. So he wanted to come visit me. I Googled him. I came up with this page. Now, this is not the version I saw. This is the one I found a couple of days ago. So it's changed a little bit. But is this the name of guy, Phil Halper, or a skydive Phil? He's really into skydiving. But I was amazed to see that he had all these long interviews with giants of physics and cosmology. He managed to get them to sit down for hours and talk about their models, from Stephen Hawking to Alan Guth to Roger Penrose, and many others. And he was actually coming here to talk to Leah Smolin and others at Perimeter. And I thought, okay, so maybe I'll talk to him. So we did talk, and in fact, this was the video that we produced, or he produced. Phil's wife, Monica, narrated it, but Phil produced it. And this was the title. You could go and find it. It's about varying the speed of light. It talks to me and to a bunch of others. I can't remember exactly who was it. Esteban Alexander, maybe. João Magoejo, maybe Leah Smolin, John Moffat, who is one of our local researchers. And when Phil was here, we talked about models of the Big Bang and this idea that, he interviewed lots of people. I've worked on different models of the Big Bang. Maybe it would be a good idea to tell people about these, because most people don't know about all the research of the Big Bang, in the Big Bang that's going on. So, in fact, most people think Big Bang was the beginning, and most cosmologists think it's not. So that was an interesting idea. We started exploring it, and then something happened. There was this thing afterwards, so we got a little bit distracted. It was a pandemic. But it was all a blur. I'm not exactly sure what happened, but then 6 years on, we ended up with this. So this is the book that came out eventually out of our collaboration. It is published as of last week. I guess you could say May 29th down there. There you go. And indeed, this was, in the meantime, some things I can remember. For example, Phil visited here. That's the two of us. And I learned a lot about Phil. So he was a banker. He made a lot of money, and at some point he retired, and then he wanted to work on his passion, which was cosmology and the science of Big Bang. So he's an amateur astronomer. He goes around the world and interviews scientists, and the more of it he does, the more people are willing to talk to him. So I think that was amazing. And the other thing is, I realized my son, at least one of them, want to be a YouTuber. So wanted to get to know these YouTubers. What do they do to get so popular? Now, I told you this is a battle. And you can imagine there are lots of challenges with writing a popular science book. So wherever there are battles, there are bodies. There are some bodies that you have to bury, but there are also ghosts that roam the fields. And if you go and actually look in Amazon, there is another copy of our book by a different publisher. So I'm not going to tell you about it, but I'm just saying there are ghosts out there. There was a battle. We survived, but yeah, there are bodies out there. Okay, so that's battle number one. Not exactly battle of the Big Bang, but battle of the Big Bang. So there's a second battle, Battle of Waterloo, I'm going to talk about. So we arrived in Waterloo 18 years ago. That's Ghazal. My wife and I both arrived as postdocs. That's not 18 years ago. It's more recent. We looked much younger back then, 18 years ago. And I was just thinking that if I was born when I arrived in Waterloo, I would be graduating high school now, probably. It would be like a graduation party here. It looks like a tough high school, though. I'm not 100% sure I would be able to graduate. But yeah, it's a milestone of sorts. So when we arrived, one of the interesting things we noticed, there was this big banner. I couldn't find an image of it online, but there was this banner that showed Waterloo was named World's Top Intelligent Community for 2007, and in fact, it was named in 2006 as well. So that was interesting, but apparently when we arrived, that streak was broken. Waterloo was never elected as most intelligent community. I'm sure there was no correlation with our arrival. And this was Perimeter Institute, by the way. So it looked a bit different. It's still as lovely, still as dreamy, but yeah, a bit different. So this is a picture that Ghazal found from the Cosmology group. We were much younger. Now that looks more like us and also blurrier. So some of the people here would recognize the younger faces there. That was in 2009. But if you go farther back, remember, we are trying to remember things. In fact, Perimeter, this building in which we are, that was first streamed in 2000 or earlier, but officially it started in October 2000. So we're celebrating the 25th anniversary. And this thanks to Mr. Mark Lazaridis. And the first research group here was, some of the members are here. Rob is sitting in front here. They look a bit different. That's Rob there. And then there is Leah Smolin, who we are celebrating his 70th birthday for this week. Fotini, Marco Polo, and then other postdocs who, by the time I arrived here, they'd already left. If you want to learn more about the beginning of Perimeter and the battles involved, again, this is the battle, you could read Howard Burton's book, who is the first founding director of Perimeter Institute. And there's a lot of fun stuff in it. But I'm not going to have time to get into it, but you could read the book or read my book, or our book. There are interesting details that you may find amusing. But one of that set of details had to do with Lee, who we are celebrating, as I mentioned. So Leah Smolin has been one of the founding faculty who's influenced the spirit of Perimeter very much. He's had 5 books that I know of for popular science, so I'm 20% of the way as far as he is. I just have 1 book, he's got 5. Or maybe more, actually, it might be missing. But it's been amazing, the road that is trodden, as Emily mentioned. I'm going to come back to 2 of these books in particular. And I'm going to talk about the battles, because building Perimeter was a battle. You can imagine this amazing institute. We see the great the great things that have come out of it, but it's taken sweat and blood to get it here. And I think we should all appreciate that. I'm going to talk about two of these books, Trouble with Physics and The Life of the Cosmos, because they're going to be very integral to the battles of the Big Bang we'll cover. Okay, so let's go to the third battle. And that's actually Battle of the Big Bang. Where did it come from? So, Battle of the Big Bang started, arguably, when in 1920s, a famous American astronomer, Edwin Hubble, used the discovery of brightness-periodicity relationship for stars, for variable stars, to measure distance to the galaxy. Basically, the idea is that if you look at this plot on the left, Ms. Leavitt realized or discovered that the stars that are variable, they vary with time in a regular way, the ones that have longer period are brighter, and the ones that have shorter period are less bright. So by finding these stars in various galaxies and measuring how their periodicity, how long it takes for them to become bright and dim and bright again, in days, you could tell how bright intrinsically they should be, and based on that and how apparent their brightness looks like, or how their apparent brightness looks like, you could infer the distance of that star. So if you have a 10-day period variable, you know it should have certain intrinsic brightness, but you can measure its brightness by taking a photograph from using a telescope, and by comparing these to the intrinsic brightness with apparent brightness, you could infer the distance. So Hubble discovered something amazing using this method that was developed by Ms. Leavitt. And, oh yeah, sorry, I should go back. Yeah. So he discovered that the farther a galaxy is from us, the faster it's moving away from us. And this is kilometer per second. So it's missing the units. Today, Hubble, if he published it, he would flank the first Physics 101. But back then, the standards were looser. So he didn't know how to use the right units there. He meant kilometer per second, and the y-axis, the x-axis here is the distance. So Hubble discovered a linear relationship between velocity and a distance. And scientists, including George Lemaitre, showed that in the theory, Einstein's theory of general relativity, that's exactly what you expect if a universe is not static, but rather expanding. So Hubble discovered that universe is expanding, and that the signature of that is the galaxies are moving away from us. But what that meant for the universe? What does it tell us? I mean, the fact that the universe is expanding tells us something about what's happening right now. But what does that tell you about the future or the past? So that was the question that fascinated cosmologists from the very beginning. And from that very beginning, there were two camps. The first camp was Lemaitre's camp, who suggested that if things are moving away from each other, so if you turn back the clock, things were closer and closer and closer, and at some point, everything must be on top of everything else. He called this primeval atom, suggested that at some point, maybe universe came out of a single quantum or a single atom. He called it primeval atom. There was an opposite camp led by Sir Fred Hoyle, image there on the top. He was a very well-known and influential British astrophysicist at Cambridge, and he thought that this primeval atom didn't make any sense. Incidentally, George Lemaitre was a priest, and Sir Fred Hoyle saw that because this sounds too much like a creationist story, even though Lemaitre didn't really want to connect the primeval atom to creation in any sense. Put a pin on that. We're going to come back to that point in a bit. Fred Hoyle thought that universe cannot have a beginning, universe must be expanding. If it's expanding now, it must be expanding forever. Why should we live in a special time? Any time is like any other time. And that's basically like a Copernican principle, same way that Copernicus said that we are not the center of the solar system. Fred Hoyle thought that we cannot be living in a special time. Any time should be like any other time. So maybe universe is a steady state. And somehow, as the universe is expanding, it's constantly matter is created out of vacuum, so nothing should be changing. Right? So past and future are all the same. That's called a steady state. So actually, I should say, Fred Hoyle called this Big Bang, and people thought that, he was trying to make fun of Lemaire's idea, the primeval atom. But apparently, Fred Hoyle said that he was being very respectful and he wasn't making fun of anybody. In fact, Fred Hoyle was also a very famous and competent science popularizer. He had his own radio show that explained various scientific concepts. And he had very lasting contribution in astrophysics, and anybody who learns about astronomy learns about his contributions. But then he didn't like the Big Bang. And the evidence came down on him at some point when this discovery happened. We discovered the cosmic microwave background. So one of the predictions of the Big Bang theory, so this was the name that later adopted by the people who actually thought about or liked primeval atom. So primeval atom was out, Big Bang now is in. And the prediction was that if the universe was hotter and denser at earlier times, then it should emit light. Like anything that's hot and dense emits light. Like the sun. Now, as the universe expands, it cools down, so we may not see things as bright as the sun, but still there should be this light that's left over from the Big Bang, that initial primeval atom, if you want. And lo and behold, there is this discovery, Penzias and Wilson in Bell Labs in New Jersey, not far from where I did my PhD. They discovered this uniform microwave that is almost the same in every direction at a temperature of minus 270 centigrades or Celsius, which is roughly 2.7 Kelvin. And they won the Nobel Prize. They didn't know what it was for a while, but eventually they talked to people at Princeton with Bob Dickey and realized that this was the confirmation of the famous Big Bang theory. So in 1978, just when I was born, I guess they got the Nobel Prize for this discovery. Now, you may think that's amazing, and that's very fitting. They confirmed the Big Bang theory, and of course, they should put Fred Hoyle in his place. But in fact, CMB was discovered by a Canadian 25 years earlier. So this is one of the biggest injustices in history. I hope Canadians are all angry for that. Americans robbed us our Nobel Prize. So if you go to this paper from 1940 by Andrew McKellar, who was in fact the president of Canadian Astronomical Society at some point, he published this paper where he measures the temperature of the interstellar medium molecules, and he measured the temperature, at least, there are uncertainty, but he measured the temperature with 2.7 Kelvin, which is exactly the temperature that 25 years later measured by Penzias and Wilson. Well, unfortunately, by the time Penzias and Wilson won the Nobel Prize, McKellar was already dead. So he died of the, I think, lymphoma. And so he couldn't win the Nobel Prize, but indeed it was, he didn't realize that he discovered the cosmic microwave background, but in fact he had. So it's actually amazing because Fred Hoyle never gave up on a steady state. One of his famous students, John Narlikar, kept working on it, so they called it quasi-steady state model. This is one of their last papers together in 1993. They're trying to explain the cosmic microwave background, but still with a steady state universe. I first met Narlikar when I was an undergrad in Iran. But then later I hosted him back in 2014 here at Perimeter Institute, where he visited for a year on sabbatical. He gave a talk about the the case for alternatives to cosmology, alternatives to Big Bang. And what he said was, you could see here in the background, there are some geese, right? And he was saying that kind of cosmologists are like geese that are flocking, like Canadian geese. They're all following this Big Bang model, and they need to think independently. It's an unfortunate turn of events that, in fact, Giant Narlikar, who was a giant of Indian astronomy and had many contributions, is very well respected in astronomy. He started Inter-University Institute for Astronomy and Astrophysics in India. He never really gave up on this assiduous state. He passed away 2 weeks ago, in 20th of May. But it actually tells you something, and if you are to learn something about here is learning about how humans do science. And it kind of reminds me of this famous quote from Max Planck, that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, a new generation grows up that is familiar with it. So it's a strange, but that's the way science works, at least one of the ways that science works. Okay, so that was the battle of the Big Bang, and you would think we're done, but not really, because you're wondering, okay, if there was a Big Bang, then what happened before the Big Bang? And that's the next battle. So what is the oldest thing you can remember? But now that we use all these tools and whistles, all the, precise astronomical observations to see down to the Big Bang, or close to it, or whatever it is, you ask what happened before. So I'm going to call it Battle of Inflation. Oh, it just went away, but Battle of Inflation. And let's kind of get to talk a bit about what is Big Bang. Okay, so I kind of thrown the word around a bit, or quite a bit by now. But let's kind of talk a little bit. So imagine that everything, as stars, planets, you were packed into a hot, dense primordial soup. And then, boom, expansion begins. Why it begins, we don't know, but it starts expanding. So there you go, that's your boom. And it's expanding, getting less and less dense. The universe grew and cooled, got colder, but then there's gravity, it took over, it made structures get stronger and denser. Eventually galaxies, stars, and life were formed. And this is actually a simulation that people do on computer, simulating the conditions at the Big Bang. Now, some of the conditions we don't know very well, but some of them are constrained by observations, and these structures we actually see in simulations and observations both. And one thing to note is that Big Bang is not something that happened at any point in space, although this simulation that I showed you looked like there was a point, but really our understanding of the Big Bang is that it happened everywhere. Everywhere in space, but there was a point in time that were around the same time that Big Bang happened everywhere. It wasn't exactly the same time, but almost the same time everywhere the Big Bang happened. So there was no center of the Big Bang. Everywhere was the center of the Big Bang, if you want. And then the science of understanding the Big Bang is understanding this picture. So this is a cartoon that we show in all our classes and our textbooks. So this is our best understanding of the universe. It is a cartoon, but it kind of shows the main thing. The universe is expanding. It's almost 13.7 billion years old. So that means that if you go back in time, 13.7 billion years, it's getting hotter and denser, and around that time, it's basically density becomes almost infinitely big. Well, that's not a very well-defined thing. If I'm in front of scientists, I say almost infinitely big. That doesn't make any sense. But here, I hope you forgive me if I say that. That's a weird thing, and that's actually what people call singularity. So there's a point where you get infinity mathematically, but physically, in fact, what happens is that your rules stop making sense. Now, that's not to say that we don't understand the Big Bang theory. we have a sitcom that tells us all about the Big Bang Theory, you think. But in fact, more seriously, we also have a theory of what happened during this expansion for most of these 13.7 billion years. So we had, as I showed you, a hot primordial soup with tiny wiggles, basically sound waves moving around. And as it expanded, it cooled down. It became neutral, and as structures start forming, you have this basically period of, we think it might be inflation or something else, where these fluctuations were seeded. Then there is this period where this cosmic microwave background was emitted around 400,000 years after the Big Bang. And then there was a dark age where not much was happening, but then the structures become dense enough that the stars started forming, and then galaxies and so on. And there is this weird dark energy, which we're not sure exactly what it is, but that's the topic for the next public talk. Okay. So you think that's a good story, but it is a story. And like any story, it has holes. It leaves room for imagination. And you may wonder, so what it is what are the holes in this story? So it tells you, I told you basically some of these details, but what caused the Big Bang and what happened before it remain a mystery. And that's the beginning of our mystery. So in particular, there are these things I showed you, I've written here. Again, we teach it in our textbooks and classes. There is inflation, singularity, quantum fluctuations. These are things that we put there as placeholders. We don't know what happened. That's a story that we tell, but we don't really see that. What we see are this cosmic microwave background, and we speculate. It's kind of we're sitting in this room, and we're trying to listen to a conversation that's happening outside. We hear bits and pieces, and we're trying to reconstruct the story or what's happening outside. But we're just listening, and we're hearing bits and pieces. And that's the situation. So there's a story of singularity, inflation, and quantum fluctuation that I'm going to tell you a little bit more about in a bit. It's only a story that's made up based on what we heard, based on these bits and pieces. So the story of singularity is actually not even an observational story, at least to most of it. It's this mathematical discovery by Stephen Hawking and Roger Penrose. Incidentally, Roger Penrose he's part of this workshop, this conference we have for Lee, and he's presenting remotely, but he was part of the discussion this morning. Stephen Hawking unfortunately passed away, but as you know, but he's visited Perimeter a lot, and he was, in fact, the new extension of Perimeter building is called the Stephen Hawking wing. So one of their claims to fame was they showed, in fact, they mathematically proved that under these assumptions that gravity is always attractive, the universe has a space, 3 space dimensions and 1 time dimension, and time travel into the past is impossible, and if you use Einstein's theory of general relativity, they proved that no matter how the universe looks like, there must have been a singularity in its past. And what is a singularity? As I said, this is this place where everything goes infinite. It's not really a physical thing. It's just a limit of understanding. It just tells you that there is this point beyond which we cannot push our laws. Our laws break down. Now, that is, again, another story. However, it turns out that all these 4 assumptions are given up by cosmologists, including Penrose and Hawking. Hawking towards the end of his life, and Penrose, if you talk to him today, they all kind of stop believing in one or another of these assumptions. So even the fact that there is a singularity is disputed, even though we don't even understand what the singularity is. So the situation is kind of weird. Let's put it that way. Now, I have, are these all kind of things I'm making up? No, we are using telescopes. We have the surveys of the universe. Okay, there you go. So, for example, the famous NASA JWST telescope can give us images of the Big Bang or universe around 300 million years after the Big Bang. But in fact, that's not the earliest image of the universe we can get. We can get to the cosmic microwave background. We can go to, let me just see. OK, so I have this image of Planck satellite that's been mapping the universe for 10 years. I think it's stopped working, but it still has the best map of the Big Bang. It's very slow, this movie. So I'm just going to fast forward to it. OK, so that's the map of that Planck has of the Big Bang. And that map is actually much younger than JWST. It's 400,000 years after the Big Bang. And that's showing how Planck satellite actually mapped this. There's a red band in the middle. That red band in the middle is the galaxy. You could ignore it. But the image on the left is 400,000 years after the Big Bang, rather than 300 million. And it shows a universe which is very smooth with tiny ripples. In fact, these tiny ripples, it looks prominent, but really there are fluctuations in this cosmic microwave background, which is 1 part in 100,000. So the constant part, I'm not showing it, I'm just showing the fluctuations. And it just tells you that you had a very smooth universe. However, the Big Bang theory I presented to you doesn't explain how it became so uniform. So this 3 Kelvin, or 2.7 Kelvin, that Andrew McCullough discovered, and then later Penzias and Wilson discovered, it's uniform to 1 part in 100,000, and yet we don't know why. In fact, there was not even enough time even for light to go from one side of the universe to the other. So how could it be so uniform? That's called the horizon problem. The story doesn't tell you what happened before the bang, and also the story doesn't tell you what's responsible for the shapes of these patterns that you're seeing. So this is, again, the cartoon made by Phil for his YouTube channel, but it's kind of showing that if you push things back to the very early time, to this singularity, basically there's a point where we don't know what's going on, and we need some sort of a theory that could explain the pattern that emerges out of the singularity or whatever that's there. So the shapes and laws that describe these patterns are a mystery. It's not that we don't have ideas. The most popular one is known as inflation. So these are gentlemen who came up with the idea, Stravinsky, Linde, and Guth. And the idea is that the universe suddenly expanded by a huge factor, exponentially, very, very rapidly started expanding. It's expanding now, but it was expanding much, much faster in a very short period of time, by 60 e-foldings, basically. So it's almost basically it's telling you that the universe within a tiny fraction of a second, 10 to the minus 32nd or so, it increased by 30 orders of magnitude in size. And then when that happens, quantum fluctuations that are tiny, ordinarily, are stretched to very large scales. And that, in fact, can explain the patterns in the microwave background that I showed you. But then inflation, as popular as it is, it has its own critics. So, for example, which inflation? Can we test inflation? There are these gravitational waves, these ripples in a space-time that's predicted from inflation, but we don't see. Should we see them? We're not sure. How does it end? And in fact, it seems that inflation never ends. There's always somewhere that is inflating. So there is this picture that almost everyone who believes in inflation endorses. Is known as inflationary multiverse, where you basically, the universe inflates on a larger scales everywhere. Some places it may end, and we may have galaxies and life and stars. But in most places in the universe, it doesn't. And you have this kind of, it's known as multiverse, different pockets of the universe where do their own things. But the universe is very inhomogeneous on larger scales. So that's another story. These are scales that are just far beyond anything we could see. It's a nice story, but there's no way for us to test it. So that upset a lot of physicists, because physicists like to test things, right? You cannot just make things up. So that led to the inflationary wars, the battle of inflation I told you. some of my friends and colleagues. So Avi Loeb on the right was one of my professors at Harvard. We worked together, and Paul Steinhardt was my professor at Princeton, and Anna Iaz, who was, I think, a student of postdoc at the time, worked together and basically wrote this article. They did a body of work, but eventually this led to this thing in Scientific American where they argued that basic inflation is not science. And then there was a rebuttal by Hawking and Witten and lots of basically big names in physics saying that no, inflation is science. So there was like back and forth, is it science, is it not science, is it predictive? Now, of course, Steinhardt has his own horse in the game, as did our old director, Neil Turok. They had a cyclic picture of the universe. So this was their model, that the universe somehow at the Big Bang bounced, and then there were these cycles of bang and basically crunch and bang and crunch and bang and crunch and bang. And they thought that this was more convincing than inflation. So there are different people. There were lots of back and forth different groups, but that was where things were, and it kind of still is there as well. So that's another battle, and if you want to learn more about it, we get much more into details and back and forth in the book. But I want to get to another battle in the last, I guess, 9 minutes, and that's actually closer to home. That's happening now in this building. And that's the battle of the strings and loops. So you can go back again. I think I did some setting that it doesn't stay very long. Battle of the strings and loops. So what is that about? So there is this quantum gravity. The idea, that's the holy grail of theoretical physics. That's what we're supposed to discover here in the next 5 years. Is that right? Or we already have it. Yeah, we got it a while back. But we're keeping it a secret. But the idea is quantum mechanics and gravity that are both very well established. They have theories of Einstein and theories of microscopic world. They just don't work together very well. I have this analogy, or kind of this example for it. I call it the Heisenberg versus Einstein microscope. So imagine there are two microscopes. The one is by Heisenberg. This is apparently Heisenberg, I've been told. Where if you want to see things better, you need high energy particles with shorter wavelengths, like photons with higher energies, like X-rays have shorter wavelengths. So you need like X-ray telescope to see tiny things, or microscope to see tiny things. But on the other hand, there's an Einstein microscope that if you want to see tiny things, you need lower energy, because if you have bigger energy, you make big black holes, and that gives you worse resolution. So there is basically this contradiction that you want to see things better, quantum mechanics tells you need more energy, and Einstein's relativity tells you need less energy. And that's kind of the problem. And by the way, this is what happened when I Googled Heisenberg. So I guess this guy was better looking. So all our basic theories fail when we reach this so-called Planck energy or temperature. And that's basically where this singularity is, that the point I was, the tip of the cone, if you want. So we have this zoo of theories that many people in this building, or many friends of people in this building, have been working on or developing: a string theory, loop quantum gravity, causal sets, asymptotic safety, causal dynamical triangulation, Hojov-Lifshitz gravity. In fact, we have people right now in this building who are doing all of them. Well, maybe asymptotic safety is someone. I still think that we have someone in this building who does all of them. And if you want to see the status, actually I have, we can go back to our good old friend, Big Bang Theory. So,
And friends support their friends, apparently. So I'm withdrawing my objection to your desire to have a relationship with Leslie. Thank you. I will graciously overlook the fact that she is an arrogant, subpar scientist who actually believes loop quantum gravity better unites quantum mechanics with general relativity than does string theory. You kids have fun.
Hang on a second. Loop quantum gravity clearly offers more testable predictions than string theory.
I'm listening. Amuse me.
Okay, well, for one thing, we expect quantized space-time to manifest itself as minute differences in the speed of light for different colors.
Balderdash. Matter clearly consists of tiny strings.
Are you gonna let him talk to me like that?
Okay, well, there's a lot of merit to both theories.
No, there isn't. Only loop quantum gravity calculates the entropy of black holes.
Sheldon, don't make that noise. It's disrespectful.
I should hope so. It was a snort of derision.
Okay, very good. And just a correction for Rob, I know string theory also does entropy of the black hole, so I hope he doesn't blame me for that. But in fact, you think that was funny, but that was all inspired. We were discussing that very fact this morning and upstairs. We have proponents and opponents and whether observational evidence there is for different energies moving at different speeds. But that's it. So they kind of stole it from us. But we are having those fights in real life. In fact, yeah, the one person in the room, Rob, is the one who's been having this with Lee, I think. It's been keeping it very diplomatic, I think. It seems very cordial. But of course, Lee wrote this book that if you see this, the caption, it says, "The Rise of a String Theory, the Fall of a Science, and What Comes Next." I should ask Lee whether he has any comment about what comes next. But I think it hasn't been as bad. We'll see. So to kind of wrap things up, there are battles happening within this building. There are very cordial battles, at least the ones that I've seen. They're good. They're constructive criticisms. There are good things happening. Maybe we could resolve the singularity with loop quantum gravity. Here I show three founders of loop quantum gravity are Leah Smolin, Abhay Ashtekar, and Carlo Rovelli. My understanding is that Abhay Ashtekar thinks the singularity is resolved. Lee and Carlo, they kind of ambivalent on that. We are former postdoc here, who actually we were together here back 17 years ago, Param Singh. He's one of the leaders and kind of leading this program of loop quantum cosmology that resolves the singularity. Martin Bojawal, though, is another loop quantum gravity person who thinks it doesn't work. So there are battles going on within that camp as well that are interesting. On that topic of resolving singularity, in fact, Ghazal here, who I mentioned, my wife, she's been leading a program. And remember I told you that one way to avoid singularity is to make gravity repulsive. Usually it actually leads to instabilities, but there's a way to actually get around that if you make sound waves infinitely fast. You would think that sounds weird, but it turns out that it works and it's okay and it's kosher. We called it coscutan, which is apparently Latin word for this thing. There's a parasitic plant there. But Ghazal has shown that, Ghazal and her students have shown that there's no singularity, there are no instability, everything is well defined. So there's another way of, other than loop quantum cosmology, to resolve this singularity. In a string theory, there are many ideas. Some of them I've worked on, some of them other people in this building. Maybe you could have a gas of strings. Maybe you could have brain words. Basically, these are these weird objects that we may live on. They're known as D-brains. And you could make cosmology with them, possibly avoid singularities. There is this idea of holographic cosmology that maybe time itself is an emergent, so it's not real at the Big Bang, it's just born somehow. So that's an idea that I worked on and tried to test it with observations. So those battles are ongoing. Not sure where they're going to go, but they're interesting to witness. There is another battle. Could we have time machines? And so this, because of the short of it is I had two friends. Rich God was my professor at Princeton. He thinks there are time machines, and he has even a replica of that up there. There's a loop where time kind of goes on a loop. Stephen Hawking thought that it wasn't possible in quantum theory, so that's interesting. In fact, we even had a model where the entire universe could be a time machine with my former student, Elizabeth Gould. I have a movie of it, but I think in the interest of time, actually, maybe Hillary, you can tell me when should I end? Few minutes? Okay. Okay, maybe I will show this to you. So this is actually a model where it's a cartoon of a model where time runs in a loop. So you kind of universe, you have the Big Bang and you have the expansion, and then you have all galaxies and all the structure, and universe becomes infinitely big, but then kind of maps to itself, which is infinitely small. And it's an infinite universe, so it's always infinite, but the time runs in a loop. And we kind of made precise predictions and compared it with observations. So we could have time machines. Maybe the entire universe is a time machine. So these are the most, okay, I'm leaving the most contentious things to the end. So hopefully you're going to bear with me, but I think these are important, and this is maybe why we're doing all of this. So there is the battle of science and religion. So we have a religion within cosmology, and this is a question that I've always thought, that you can take cosmologists out of religion, but can you take religion out of the cosmologist? No. Without evidence, empirical evidence, don't we revert to religious dogmas and crusades just under noble guises? And then I mentioned some of these. We have trouble with physics. We have people think that the string theory is right without any evidence, and people think that it's the end of science. And I do wonder that can we ever rule out the string theory or loop quantum cosmology or loop quantum gravity or inflation the way things are going. So I think there is that. But there's also cosmology within religion. There are religious advocates who are arguing that the Big Bang theory is evidence for existence of God. So this is the Kalam cosmological argument that says that there must be a beginning of time, so there must be a cause. But we talked to you, there is no guarantee that there's a beginning of time. So we don't know. The singularity theorems work only within their assumptions, and nobody believes their assumptions anymore. In fact, we did this survey for 80 physicists in a conference and asked whether Big Bang tells you that there's a beginning of time. And there are only less than 20%. 68% said that Big Bang just says that the universe was denser in the early times. So nobody really believes in the beginning of time. Whether there was a fine-tuning by an intelligent design, but it turns out there are alternatives. There is this multiverse of various possibilities, and you may have natural selection, we can live. Or in fact, there is this wonderful idea by our colleague Lee. He calls it cosmological natural selection, where you make universes inside black holes, and then each black hole could have its own life and make its own offsprings. And the parameters may be just fine-tuned with, it's not really fine-tuned, it just evolves to form more and more black holes. So, and then you wonder, are we doing pseudoscience or proto-science when these things are happening? And it's not clear, right? And I've been in all of these arguments on both sides. There is no exact demarcation criterion. So science is imagination in a straitjacket, but it takes time to see where you are and whether you fit in that straitjacket or not. So I've run over time. Sorry, I thank you very much for bearing with me. And I'm going to leave you with the final battle. So the final battle is that the nature will guide us. So the future, I don't think is perpetual battles. The future is that we're going to learn from the universe, and it's going to teach us. We have these amazing experiments that are mapping the universe, the more cosmic microwave background, more galaxies, orders of magnitude more of both. And we may even see gravitational waves from the Big Bang. So there are these amazing experiments that are either in process or in planning, and they're going to tell us much, much more. And hopefully, at least the things that are testable are going to be tested. And the ones that are not testable, hopefully they will be shamed to become testable. So the real battle is not really with our colleagues in this building or outside, or our fellow citizens. Our true struggle is to overcome our ignorance, our adventure to comprehend the cosmos, ourselves included. So we are part of the cosmos. So our process is a scientific method. It's honed on solving cosmic mysteries, but also derived from all other aspects of our humanity. We are not distinct from our humanity, and all aspects of our humanity, from art to religion, is part of our science. We cannot ignore them. We have to embrace them. So this will be our ultimate survival tool, our scientific method, that is our ultimate survival tool in an ever-changing world. So the power to remember our past lies in your future. Thank you.